Now the question. Yeah. This question, when we apply the choice rules, we should use the right way to apply the choice rules. Yeah. First, give you the answer. This B term is not redundant. It is necessary. It is necessary. Okay? It does not violate the sum rule. Yeah, why? B term does not violate the sum rule. It's not redundant. Yeah. Here, to see that answer, we need to double check, go back to the choice rule. Yeah. Let's read the choice rule carefully. Okay? Yeah. Just the basic part. Yeah. We only need to double check the basic rule A. Yeah. Rule A in the choice rule. Rules. Yeah. Yeah, let me get out and get to the choice rule page. All right, yeah. This one. This one, okay? Yeah, yeah. Here I do not need to put it in the slide mode. Yeah, let's just look at the slide here. All right. Basic rule. First column, our function, yeah, this time it's a monomial, right? Yeah, actually a polynomial, two terms, polynomial. But let us look at the highest term. Highest term in that one, it's a kt squared, right? N equals 2, kt squared. When you have a term kx squared, yeah, tx, just a variable, right? Yeah, yeah. Here it's x squared. Kx squared, what should you use here? It's a whole quadratic polynomial, right? 3 terms. So that one term, t squared, in order to take care of that one quadratic term, you already need 3 parameters. Yeah, all 3 undetermined coefficients you need. Okay, that one term you already need 3. Yeah, that for other terms, yeah, you're still 3, right? Yeah, still 3. Okay, yeah. So based on this rule, yeah. So we use ABC, no redundancy. So they are really necessary. Okay, no redundancy. Yeah, that's the main point. Okay, yeah. So that means this function a little special. Okay, yeah. For other functions, sine, cosine, also special. When you have a cosine, then the second column you should have both sine, cosine, not just one. Okay, you should have both sine, cosine, because derivative sine comes out, right? When you do derivative, sine comes out. So you should, when you have one cosine, you should have both. One sine, you should have both. We have sum of sine, cosine, you still have both. Yeah. Yeah. Things like that. Yeah. All right? Yeah. So when you apply the choice rules, try to be very careful. Yeah. All right. So we answered that question. So we can continue our solution. Then the calculation part, I think, should not be hard. Yeah. The calculation part. Yeah. Pretty straightforward, yeah, actually, the calculation. So here you can see for the choice rule, the critical step is YP. How do you write YP? If you get it right, remaining just, calculation. Yeah. All right. But here I need to change my pen color. Yeah. Every time I need to change. All right. Yeah. 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 Just a simple calculation. Yeah. It's not too hard. Yeah. Yeah. Set of equation, then compare corresponding. Yeah. But yeah. So for this one, for this case, B happened to be 0. Yeah. Yeah. So this B happen to be 0. Yeah. Let me ask you another question. Yeah, because based on our calculation result, b equals 0, can we say this b term is redundant? Can we say this b term is redundant? B equals 0. After calculation, b equals 0. It looks like redundant, but when you make this conclusion, there is some potential problem you may not be aware of. If you are aware of it, then you are fine. But if you are not aware of it, you may have problem. The thing is this. Look at here. We have an undamped system, right? We have an undamped system. Think about if you have a damped system, what would happen? You may have a damped system, right? If you have a damped system, you have a term, yeah. So let me use a constant rho times y prime. How about that? That's the damped system, okay? Yeah. When you have a damped system, then your b won't be 0, right? Yeah. Then your b won't be 0, okay? Yeah. So, yeah. So if you are aware of this problem, so then you can get it right. Otherwise, if you base this example, you make a conclusion that b term not necessary, but you may have a damped system. Then you cannot ignore the b term. Okay? Yeah. All right. Yeah. So that is the yp for the first piece. Yeah. So that function. Yeah. First, we have two pieces. The first piece. All right. So the general solution, capital A, capital B. Yeah. All right. That we need to determine capital A, capital B by the initial conditions. Yeah. So plug in initial conditions. Yeah. Yeah. Very easy. You can find capital A, capital B. Right? Yeah. B 0. Okay. Yeah. That's good. So you get a very simple solution, but on the interval between 0 and a pi interval. Yeah. So between 0 and a pi. Yeah. The first piece, but you also need to calculate the second piece. Okay. All right. Second piece, only solve this very simple homogeneous equation, sine cosine. Okay. Determine CD. Yeah. Yeah. All right. Determine CD. What appropriate initial values you want to use? Yeah. Initial conditions here. Pi, initial condition. Yeah. Pi. Yeah. Pi, you plug into this solution, right? So what's the y pi? You plug in t equals pi. So yeah. So you get this number. But what is the y? Yeah. So here the question. Y prime of pi, you take a derivative, then you plug in pi. But the question, so here the question, all right. Yeah, so because you take derivative, yeah. You take derivative, so that, yeah. But actually, yeah, so here, yeah. So let's complete it, yeah. For this second part, second piece, do you have any question? For the second piece, if we solve this way, do you see any problem? No. Because, yeah, so let me describe this for the second piece. So first piece, no problem. Yeah, first piece, perfect. Yeah. So no question for the first piece. But for the second piece, then we should be very careful. All right. All right. This equation has no problem. Okay, first, this step. This equation and the general solution has no problem. Capital C, capital D. So the last thing we need to be very careful is when we determine capital C and capital D, we need to do things very carefully. Yeah. All right. Initial condition. Y of pi, that's the initial condition because second piece starts from pi, point pi. Okay, that's the initial condition. Y of pi. Yeah. No problem. Yeah. F function is a continuous function, right? From the picture, F function is a continuous function, right? Yeah. Yeah. All right. F function is a continuous function. All right. But the question, F function, its derivative is not continuous, right? Its derivative is not continuous, right? No, F function. F function is continuous. Can you see the derivative of F function is not continuous? Look at it. Look at the point. We know derivative related to tangent line, right? Derivative is the slope of tangent line, right? That's the geometric meaning of derivative. When you have a curve, how to see the derivative? You draw tangent line. Then you look at its slope. The slope is the derivative. Yeah. Here, let's use the slope to understand derivative. All right. There are two pieces. Let's draw the tangent line of the first piece at this pi point. Tangent line. Is it tangent line like that? There is a slope, right? This line has a slope, right? Then the second piece, the tangent line, the same line, right? Horizontal, right? Yeah. So the slope 0, right? Can you see these two slopes are different? If the slopes are different, that means derivative is not continuous. F function, its derivative is not continuous. All right? Yeah. All right. Yeah, so we see this fact first. Yeah. All right, second. When we calculate y of pi, we plug in t equals pi, we use the solution of the first piece, right? We use the solution of the first piece. But the first piece and the second piece, there is a intersection, one point, yeah, at pi, yeah, the same. The first piece and second piece, they share the same point at the pi. Okay? Yeah. So we know this point belongs to the first piece, but it also belongs to the second piece, right? This pi point belongs to both pieces. Okay? Yeah. Why we can use the value of the first piece to be the initial value of the second piece. Yeah. So this is the value from the first piece. Why we can use the value of the first piece as the initial value of the second piece? This is second piece. Okay? Yeah. So that question. So here, the second piece. All right? Two different functions, second piece. Because here, obviously, we use the y of pi from the first piece as the same initial value for the second piece. Why we can do it? Because y function is continuous. If y function is continuous, can we do it? It's a continuous function. Two pieces, when they join at one point, if they are continuous, they have the same value, right? Yeah. So we use the continuity of the y function. Right? All right. All right. Then, the second step, we need to answer the same question. Okay? Now, we calculate the y prime of the first piece, right? Yeah. Here, because this place, we calculate y prime of the first piece from this the solution of the first piece. We get this y prime. Because second piece is CD undetermined, we cannot calculate y prime, right? Yeah. We can only calculate from the first piece. So y prime of pi from the first piece, while we can use the same value as one of the initial values for the second piece. While we can use y prime of pi from the first piece as the same initial value as the second piece. Is there any problem to use it? Is there any problem to use it? Okay? All right. If you look at the f function, it is continuous, right? No problem. Okay? But its derivative is not continuous, right? Yeah? If the derivative is not continuous, that means, yeah, here I'm talking about the f function first, okay? Let me talk about f function first. If we calculate the derivative at the pi point of the first piece, we cannot use it as the derivative value of the second piece, right? Because it's not continuous. Okay? For f function, you cannot do that. You cannot use the derivative of the first piece as the derivative of the second piece because it's not continuous. Right? Yeah. All right. Here, but we're talking about y function, right? Not for f function. That's different. Here, we're talking about the y function. Y function has different property from f function, right? Yeah. So for y function, can you tell me, is the derivative of y continuous or not? If derivative of y continuous, then you can do it, right? Yeah. If y prime is a continuous function, then y prime of pi from the first piece is the same as the y prime of the second piece at pi, right? Because they're continuous. Okay? So here the question is, can you convince me that y prime is also continuous? Continuous or not? Yeah. All right. Yeah. So one way to see it, we want to find y solution for two pieces, right? Yeah, we want to find y solution for both pieces. All right, solution. All right. For the both pieces, here you see y double prime. Y double prime, that means y function, its second derivative must exist, right? The second derivative must exist. If the second derivative exists, the first derivative must be continuous. Because the first derivative must be differentiable, right? Yeah. You have second derivative, then the first derivative must be differentiable. Differentiable function must be continuous, right? Can you imagine if a function is not continuous, how can it be differentiable, right? Differentiable property is much stronger than the continuity, right? Yeah? You know, first derivative already differentiable. So it must be continuous, right? Yeah. So from that point of view, you know, y prime must be continuous. So you can do it in that way. All right? Yeah. Yeah. So here we try to, you know, when we join two pieces, we try to be very careful. Okay? Yeah. Two pieces. At the join point, we need to check the conditions carefully. Yeah. Can we do it in this way? Yeah. All right? Yeah. All right? Yeah. So, yeah. Let me stop right here. Yeah. Do not spend too much time. Yeah. Here. Just here, review some, basic properties of calculus. Yeah. All right. Yeah. E.3, then solution by variation parameters. Yeah. So that's the main topic here. Yeah. So we need to learn this special problem-solving idea. So this is a, very useful problem-solving idea. So let's try to understand this technique. Yeah, it could be very useful. Later in the similar situation, you can apply this same technique. Yeah. All right, method of variation parameters. Standard form. This time, we consider the P function, Q function. This time, not necessary constant, right? Yeah, constant too restrictive. Yeah. Now we can consider non-constant P function and a non-constant Q function. Yeah. Then it will be much harder. Yeah. So you can see, to solve this problem with non-constant PQ functions, how hard it is. Yeah. So you really need some non-trivial technique to help you find the solution. Yeah. Yeah. So this technique, because our goal is YP. Okay? All right. Y. Yeah. Yeah. Homogeneous, so here we assume Y1, Y2 can be found from the homogeneous. Yeah. Yeah. For the homogeneous, we did it, right? Homogeneous. Did we do it in the previous parts? Yeah. Yeah, but actually not. Previous we did constant, but for PQ, non-constant. Yeah. Yeah, non-constant. Yeah. All right. Yeah. So here, assume two basis functions. All right. So probably we will do it right here. All right. Yeah. Because as I remember, we didn't do it for PQ, non-constant PQ. All right. Now variation parameters. Okay. All right. Consider the general solution. All right. Yeah. So here we want to get inspiration from the constant case. Yeah. So when PQ are constant, we can find Y1, Y2 function, right? Yeah. After we find Y1, Y2 function, so we can write the general. Yeah, but here, even if PQ non-constant, if you can find Y1, Y2, you can still write your general solution YH in the linear combination of Y1, Y2, right? Because it's linear, right? This is a linear, homogeneous ODE, so there is that linearity principle, right? Yeah, we apply linearity principle. So we can write general solution in this way. Yeah. All right. Yeah. Yeah. So here, there is some important step from this one. Yeah. So simple. Yeah. All right. Here, look at the title, variation parameters. Variation parameters. All right? Yeah, variation parameters. So here, constant parameters. Constant parameter fixed, it's not a variation parameter. Okay? It's fixed. So variation parameter means we need to change the parameter part. Make it a variation. make it undetermined functions. Yeah. How do you make it a variation? Function. Function form represents variation, right? Yeah. Constant form, not a variation, all right? Yeah. Function form. So here, that means you replace C1, C2 by two undetermined functions, okay? All right. So we use U function and a V function to replace C1, C2. Yeah. In order to calculate YP, yeah, so we use U function and a V function. To be determined, okay? Yeah. So here you can see when mathematicians develop this technique, yeah, so they really need to use their imagination. Yeah. So there is a big jump from this step to this step. Yeah. Change from constant to function. Replace a constant by a function. Then you have more freedom. When you have a function, you have more freedom to make the change, right? Yeah. Constant, too restrictive. You cannot do too much. Yeah. So now, suddenly, you have a lot of freedom to manipulate your formulas. Yeah. So that's the reason you go from that step to this step. All right. Then, here we assume y1, y2 known. Right? Yeah. But how to find y1, so that's another question, right? Yeah. So later, yeah, we try to, find the y1, y2. Yeah. So here, assume y1, y2 known. We want to find yp. That's our goal. All right. To make it a particular solution, our original, then we need to plug into the original solution, right? Yp. You plug in. Okay? Yeah. All right. Yeah. So let's do the calculation. This time we need to, do some hard work. Yeah. Yeah, because when you take derivative of yp prime, there are 4 terms by product rule, right? Product rule on the first term in yp, you have 2 terms. Product rule on the second term of yp, you have another 2 terms. Total, you have 4 terms. That's quite a lot. 4 terms. Hard to control. Too many terms. Yeah. Too much variation, right? Yeah. So the good thing about the variation part is you have more freedom. The bad part is you have too much freedom. You have to, at the same time, you have too much uncertainty, right? Yeah. In problem solving, we don't like uncertainty. Yeah, people like certainty, more certainty. Yeah. Uncertainty, too much work. Yeah. All right? Yeah. So here, that's YP. YP. How about the YP double prime? Yeah, because we need to calculate YP double prime, right? Is this scary? Calculating another round double derivative on this representative. Is this scary? Yeah. Because if you apply product rule, you have 8 terms, right? Yeah. Each one split to two terms. Total 8 terms. Yeah. So do you have an idea? Well, because we have to calculate yp double prime. You cannot avoid it. Is there any better idea at this step? Let's pause a little bit before we go to the next very messy round calculation. Can we do something a little better?
I think I remember. Do we pull out the prime, the U prime terms and the V prime terms?
Yeah.
And save them for later?
Yeah.
I think so.
All right. Yeah. All right. So the idea is, at this step, before we go to the next step, we want to reduce the number of terms. We want to reduce number of terms because 4 terms too many. So here, how can you reduce term? Because we have a lot of freedom, right? can we apply the freedom we have to reduce 2 of the 4 terms? Make 2 of the terms disappear. Is it possible? 2 of the terms disappear. 1 term you cannot make it disappear, right? 1 term. But two terms, can you make 2 terms just cancel out each other? 2 terms cancel out, right? 1 term you cannot cancel out, right? 2 terms, if things are right, you have a chance to cancel out, right? Can you use your freedom to make it cancel out? You have a lot of freedom. You use your freedom to make it cancel out. All right, that's the idea. All right, 4 terms here, too complicated. Yeah. So now we want to simplify it. Okay. Yeah. All right. So simplify the 4-term expression. Yeah. We try to cancel. Make two terms, just cancel out each other. All right. Yeah. How to simplify it? Yeah. All right. Let's group them. Grouping. So here, yeah, in problem solving, grouping is a very important manipulation method. When you do appropriate grouping, so you can explore some interesting properties. Here, let's do grouping in this way. Yeah. Here, yeah. So this u y1 prime, v y2 prime, u prime y1, and v prime y2. Yeah. All right. Now we can make assumption. Yeah. In problem solving, we can make assumption. If your assumption is reasonable, you can do it. Yeah. If your assumption is reasonable, yeah, you can do it. Yeah. Yeah. If your assumption may cause contradiction, then you cannot do it. Okay? Yeah. So, all right. So here, so our assumption, we want to make this part, second parenthesis, to be 0. We assume it's a 0. So here, the question is, because at this point, this assumption is, when you make this assumption, you need to think about, is it too much assumption? Yeah. You assume too much. Yeah. That could happen. Yeah. So, but here is, because we have a lot of freedom on u function and v function, the question is the amount of freedom we have is big enough to allow us to make this assumption? Right? That's the question. If we have a lot of freedom, we can do a lot of things, right? With the freedom. So the question is that a lot of things we can do include this assumption? We don't know the answer, right? Yeah. You don't know the answer. But is there a possibility? There is a possibility, right? Yeah. So under this situation, then, as mathematicians, the researchers, under this situation, so their, brain, so they take this kind of mentality. There is a possibility, but you don't know if you can make it or not. Just do it. If you can get through, then you make it. Okay? Yeah, just try it. Yeah, because there is a possibility, right? So then we try it. Yeah. Now, this assumption, we can make it or not, we don't know. But let's just do it. Let's take this assumption. Then we want to solve, we want to make a YP, satisfy the original equation and find a solution. Yeah. All right. So let's just do it. All right. Yeah. So then YP prime, now 2 terms, right? the last two terms is gone. Yeah, but here you have two equations, right? You have that equation, then you can take double prime, right? Double prime yp. So let's continue the remaining calculation. Double prime, 4 terms. Yeah, although still a lot of terms, but much better than 8 terms. Yeah, all right. Yeah, now our variation parameters. Yeah, because that's our assumption. Yeah, so we can use it. Yeah. Yeah. Hopefully, no contradiction. In our calculation. Yeah. All right. So yp prime. Yeah. And that. All right. Yeah. So here. Yeah. So here we do because we want to calculate the left-hand side of the original equation. So we need a p times yp prime. Okay. All right. Then q times yp. All right. Yeah. Right. Add them up. All right. Then combine the terms. U times parenthesis, V times the parenthesis, then some extra terms, all right, yeah, from the calculation. Yeah. But the y1 is the solution of homogeneous equation, right? Yeah. Y1 solution of the homogeneous, is this gone? The first parenthesis disappeared. Yeah, because y1 is the solution. Homogeneous part, then the first parenthesis equals 0. That's the homogeneous version, right, of the ODE. So y1, yeah, so the first parenthesis disappears. Second parenthesis also disappears. So we have this, at the end, we have this much simplified equations, right? Yeah, see? Assumption 1, yeah, that is assumption, right? Yeah. There, the original ODE, after simplification, we get a second equation here. Okay? Yeah. So next, we only need to solve this simplify. Not too bad, right? Solving this equation, not too bad, right? Yeah? Yeah? Yeah. It is so this is a linear system with 2 unknowns, right? 2 unknowns. Yeah. Yeah. U prime function unknown, V prime function unknown. 2 unknown functions. Yeah. Or here we can treat as unknown variables. Yeah. Because function variables, same thing, object. Yeah. We treat as object. Yeah. All right. Then y1, y2, y1 prime, y2 prime, we assume known, right? Yeah, we treat as known coefficients. y1, y2 known, y1 prime, y2 prime known, are known. So u prime, v prime unknown. Can we solve this linear system? We can solve the linear system, right? Yeah. 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 So we apply, so we can write this matrix version of the linear system. This is the matrix version, linear system. Okay? Can you find the solution of this linear system? Yeah. So here we need to use linear algebra a little bit. Yeah. Because this, all right, let's look at this 2x2 matrix. Yeah, here, yeah. 2x2 matrix. Is this matrix invertible? Is this matrix invertible? Yeah, because we want to take inverse of this matrix, right? When we take inverse of this matrix, we can find u prime, v prime, right? Yeah, inverse. But when you take inverse, how do you know this matrix is invertible? Can you see it? The matrix is invertible or not? Because y1, y2 solutions, they must form a basis, right? Yeah. When we find the homogeneous solution, y1, y2, they must be 2 functions in a basis, right? Basis, the 2 basis functions must be linearly independent, right? Two functions in a basis, two basis functions must be linearly independent, right? Yeah. Linearly independent. Is this the wrong scale of these two functions? Y1, Y2, it's the wrong scale? Yeah. It's the definition. If you calculate the determinant of this matrix, the wrong scale, right? Wrong scale of two linearly independent functions must be non-zero, right? Yeah. If the determinant is non-zero, then this matrix is invertible, right? Yeah. The invertible, the condition for matrix to be invertible, determinant is non-zero. That's the condition for invertible matrix. All right? Yeah. So that's our, linear algebra, basic knowledge. All right. So here, but here, I do not go that way. Here, we can solve it directly. How about that? Yeah, because this linear system is very simple. So let's multiply the first equation by y2 prime and the second equation by y2. Then we do cancellation. Yeah. All right. So we do subtraction. The first one minus the second one. Then this w is the wrong scale. Okay? Because when you do subtraction, one term you can cancel out. Okay? y2 prime, y2 prime, y2. This term can be canceled out. All right? Yeah. So then this u prime, then the parenthesis part is the wrong scale. W times u prime equals here, negative ry2. Then w we can calculate. So we assume w is known. So u prime is this expression. U prime, we can do the integral to find the u prime, right? Yeah. So then to calculate the v prime, but we do a different operation. So y1 prime times first equation, y1 times second equation. Then we do subtraction. So negative. So the v prime, we can find it out. Okay? V prime, we can find it out. Then we take integral. U, negative integral, the function inside the integral is known, right? y2 known, r known, w known. Yeah. So we can calculate this integral. V function, y1 known, r known, w known. So we can also calculate the v function. So we can find both u and v. Yeah. U and v can be calculated. So here you can see if you know y1 function and the y2 function of this, the homogeneous, second order linear ODE, then you can apply these two formulas directly, yeah, because we went through the whole process. You do not need to go through the whole process every time, right? You just apply the final formula, calculate the u, calculate the v. Okay? Then you can write your yp. Yeah. After you do the calculation, then you can write the yp explicitly like this. Yeah. Yeah. So this whole problem can be solved. This whole problem can be solved. Yeah. Although the computation of the integral could be a little hard. Yeah. But you can use online calculators, right? You're allowed to use, online calculators. Yeah. But if it's too hard, because sometimes the calculator may not be able to do it, you just leave there. Okay? Yeah. You don't have to find a beautiful final formula. Yeah. Because in the real world situation, yeah. So here we talk about in the real world situation, when you derive this formula, the integral cannot be calculated in a clean, nice, beautiful way. Don't worry. In that situation, you can apply numerical calculation. Yeah. Integral can always be calculated numerically. Yeah. We use the software. Use some software to calculate integral in a numerical way. Yeah. Then, solving engineering problems, that's good enough. Yeah. Because our goal, we want to solve engineering problem. So the numerical solution is acceptable for engineering problem. Yeah. All right? Yeah, okay, let me stop right here. We have a few more slides for this part, but we finish most part of our module 2. We have part F about PDE, so I need to do it next week. So this week, I plan to give you quiz number 2. And then next week we definitely complete module 2. So I will give you homework number 2, targeting module 2. Yeah, module 2. Yeah, and one student also asked me to post some exercise questions for module 2. Yeah, so this week I will post a few questions similar to your module 1 exercise questions. So let you practice before. Next weekend, I will assign second. So you have 1 week, period, so you can try that exercise questions, module 2. Yeah. All right, that's it.